In this lecture, we're going to talk about quotient spaces. And this is an elementary, I don't know, but this is a topological notion. And the topological notion is important because many of the manifolds we make are actually going to be defined as quotient spaces. For example, the Mobius strip, which is a good example I really do want to get to. The Mobius strip is a perfect example of a quotient space. And then there's the projective plane, which is a good example of a manifold that can be understood as a quotient space. The cylinder is a manifold and that can be understood as a quotient space. So can the sphere. Matter of fact, almost everything that we deal with can be described as a quotient space. And what's really important is that in general relativity, if you may remember these images that you get of the Kerr space-time, where you're patching together different pieces of space-time in along lines where you sort of blend different maps together, those are all understood in a form of a process called gluing. And quotient spaces is really the definition of what gluing is. You'll never understand gluing unless you understand quotient spaces. So we're going to begin with a study of what quotient spaces are. And what's also nice about it is we get to review a lot of our core topological notions that we've covered in the previous lectures. So let's begin. We'll start with this notion of an equivalence relation. An equivalence relation. And I'm going to just do this through an elaborate example that will follow us through the course of all of our work today in various forms. But we're going to start with the real line, and I'm going to break the real line into intervals of 2 pi on both sides of 0. And once we do this, we are going to, this is just the real line, and when we talk about the real line, we're always talking about the real line with the usual topology. That's the standard topology of one-dimensional open balls. And when we look at this, I'm going to identify a single point on this line. I'm going to put it right there. And I'm going to call that point x, I'll call it, let's say xi. And I'm going to create a relation between xi and other points on the line, and that relation is ultimately going to be an equivalence relation. I'm going to say that xi is equivalent to xj if, and only if, xj equals xi plus 2 pi times kj, where kj is an element of the integers. So if xi is the point that I've identified here, the xj's that satisfy this relation here can be easily plotted on the line, and which is why I chose this as an example, by just adding 2 pi to xi. So for example, that would put it right here, for example. Or by likewise subtracting 2 pi from xi, which would put it right here. And what this equivalent relation is saying, or what this relationship is saying, is that xj, if I can find an integer in the element, if I can find an integer where that makes this true, then xj is equivalent to xi. And this is going to be an infinite number of equivalences. Right? There's going to be another one here, and another one here, and another one here, and it's going to be infinite. It's going to go on both sides of xi forever. And this would be an example of xj, and this would be maybe say xk. And we could actually make it very simple, and we could call that x0 and x1 and x2, where the subscript now actually equals the value of k that we're using. So this one here would be x minus 1, x minus 2. And so this is what we're going to say is an equivalency. Now it's not quite enough, right? Just having a relation is insufficient to call something an equivalence relation. this relation must have a few properties that are very, very critical. They look a little obvious, but we have to run through them. For example, one property that an equivalence relation must have is that xi must be, an equivalence relation we create a symbol for. Xi must be equivalent to itself, right? Notice that you can't replace this with an equal sign, right? This says one number is equivalent to another number. Doesn't mean that they're equal. In fact, here you know that they're not equal. Xj does not equal xi. So equivalence doesn't mean equal. It means we are just establishing the notion that these guys are equivalent. We're creating this new notion of equivalency, but it is not the same as equality. But xi is equivalent, I got to get this right. So going back here, one thing that has to be true for an equivalence relation is that xi must be equivalent to itself, right? Which is true here, because if I choose k to be 0, then xj does in fact equal xi, and xi will equal itself. So everything must be equivalent to itself for the relation, which is this, to be an equivalence relation. The other thing is very relatively, well, nothing's really obvious, but if xj is equivalent to xi, then it must be true that xi is equivalent to xj. And for our example equivalence relation, this holds true because I can solve this for xi and I'll get another integer k, and that's all you really need. Is to so xk is equivalent to xi through the integer -2, right? So this is also true. And then one other thing you need is something called transitivity. So you have to say if xi is equivalent to xj and xj is equivalent to xk, then xi is equivalent to xk. So this is the reflexive property, this is the symmetric property, and this is the transitive property. And these three things have to be true to have an equivalence relation. And indeed, the equivalence relation I've specified satisfies all three of these things. And the equivalence relation is going to be our foundation for our construction of quotient spaces. And it's always going to be through something, well, it's going to be through what we call equivalence classes. Equivalence classes are sets. And they are the sets of all the points that are equivalent to each other. So I write that as in this form. I write an equivalence class. I would write x0. x0 is an equivalence class, and as I said, it equals a set. And that set is the set of all points equivalent to x0. So it's going to be x0. It's going to be x plus or minus 1, x plus and minus 2. So these here represent 2 points each, right? The plus point and the minus point. I'm just trying to make it a little efficient. X plus and minus 3, forever and ever and ever. So this equivalence class is a set of countably infinite number of objects, but it is, this symbol here is intended to mean this set of points. And what's important to see is that this equivalence class doesn't pick out every point on the real line. It only picks out these points here in red. So I would have to identify another point, maybe yi, and I could put that, say, here, and yi would be, let's see, you know, I'm treating these as though they're pi, but it's 2 pi k, right? So there's one here, there's one here, there's one here, and for the red points, there should be one here and one here, right? Something like that. So so every 2, because every 2 pi, right? Every integer times 2 pi. So it's plus 2 pi plus another 2 pi plus another 2 pi. So yi will have its own equivalence class, and it won't be the same unless, well, I call that y0. It won't be the same unless y0 happens to equal x0. And one important thing about equivalence relations is that if you have a true equivalence relation on a set, then the complete set of R is going to equal the union of all the equivalence classes, where X is an element of the interval 0 to 2 pi, open like that. So the and every element of R is only going to be in one equivalence class. This says that the equivalence classes partition R. Now, I don't have time to go into the deep proofs of all of this, right? I mean, it's not a very difficult proof to show that equivalence relations form equivalence classes. Equivalence relations form equivalence classes which partition the underlying set. But that's a kind of a basic notion of set theory. But it is important to know. So we can now, each equivalence relation will create these equivalence classes. And that is essentially our starting point for producing a quotient space. There are a few other notations. Sometimes equivalence relations are expressed with a letter, and sometimes that letter is R. So I would say X is related to Y would be the same as writing X is equivalent to Y. Sometimes you see that. And sometimes you'll also see it combined. You'll see X and you'll have a little R next to the tilde that shows the equivalence class, that shows the equivalence relation, because sometimes you'll be dealing with more than one equivalence relation. And sometimes you'll even see X, the equivalence class, and some kind of symbol to note what equivalence relation you're dealing with. And sometimes the equivalence relation is just, if it's unambiguous, is just identified by the little symbol here, this little tilde. Other times they give it a letter, and of course, I mean, you could, and if there's a lot of different ones, sometimes you'll have a double tilde, right? That's another option I've seen out there. I've seen you have one equivalence relation, X is equivalent to Y, and another equivalence relation, which might look like this, X equivalent to Z, with two tildes. I mean, there's a lot of different notations. This actually is not too uncommon with the big R. So the way we create a quotient space is, hold on. The way we create a quotient space is we are now going to create a map, because with this equivalent relations we have the ability to make a map. I'm going to now not label this line as much, but these intervals in the line are regular intervals, whether they're 2 pi or later on we'll treat them as integers for simplicity. But once we have this real line, and when I say the real line, I mean the real line with the real topology. It's very important. You'll see why, but carrying around the topology is always implied, but it's really important to stipulate in the way we're studying this now. But now you can imagine a map from this real line to another space, which I'm going to call the quotient space. And the quotient space, in this case, is going to be with the equivalent relations we had before, which was xj is equivalent to xi if xj equals xi plus 2 pi kj, where kj is an element of the integers. That map, you know what, I'm going to call it P for projection, and it's going to map every point to its equivalence class. So P is going to map the point X to the equivalence class of X. So the quotient space is actually a set of all the equivalence classes of every point on the real line. And I can't even I can't write them down in any countable way, right? Because there's just an uncountably infinite number of them. So I should write it down this way. I should write, let's call the quotient space I'm going to call it R star, which is a little risky because that looks like the dual of a vector space, but a lot of books use R star. Well, you know what, better yet, I'll tell you what, we'll just use the right language, which is R quotient, the equivalence class. This is the symbol that is used for a quotient space. It's the underlying space with a slash and then the equivalence relation that makes the quotient space, the symbol for the equivalence relation. In this case, we're using the symbol tilde. And so this is actually going to be the set of sets, right? So what I've just written here would look like the set of 0 plus or minus 2 pi plus or minus 4 pi, etc., 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 and then some other number x, and then it's x plus or minus 2 pi, x plus or minus 4 pi, forever and ever and ever. And I need this for every single point on the real line. It's kind of silly for me, and I probably shouldn't be trying to list them because it's not countable, right? That means there's no countable number of x's, right? I put down x1, I guess I need a little comma in there, right? Oh, yeah, the number x, comma, x plus 2 pi, x plus 4 pi. But it's an uncountable number of these things. And in fact, there's one equivalence class for every point starting at 0 and going to, let's call that pi, call that 2 pi, right? Starting at 0 and including 0, going to 2 pi but not including 2 pi, because 2 pi is its own, 2 pi is the same equivalence class as 0, right? So the way I would, so every one of these points here is going to have a representative of every equivalence class in the quotient space, right? Now that doesn't mean that this interval, it doesn't mean that this interval here is somehow homeomorphic to the quotient space. All I can say is that it has the right number of points, right? It has the right number of points. But whether this interval is actually what the quotient space is, whether the question is what is the quotient space, right? That's what we ultimately want to get to. We understand the real line well because we know what the set is and we know what the topology is. The quotient space we understand as a structure. We understand it is the set of all the equivalence classes of the based on this equivalence relation. We got that. The question is it as a topological space, what is it? Because we just know what it contains. We don't know what its topology is. So it's not, right now, it's not even a topological space. But it is this set of all these equivalence classes. And in this case, it's an uncountable affinity of equivalence classes, one associated with each point between 0 and 2 pi. And by the way, it could be any integer in 2 pi, right? It could be, 17 and 19 pi, right? That would be the exact same number of points, and sure enough, 18 pi, right, is going to be equivalent to 0. So the equivalence class for 18 pi is equal to the equivalence class of 0. Right? So it doesn't matter what interval we choose as long as we get all of the points in there. And that is what we call the quotient space. And this map P is called a variety of different things. It's the projection. It's also called the canonical projection. Oops. It's also called the canonical projection. Or it's also called the natural projection. And the reason they use these words canonical and natural is because once you have an equivalence class, you don't have to think hard to get P. You don't have to do anything else. The equivalence class is the existence of an equivalence relation creates these equivalence classes, and the map is obvious. Once you have this, there's only one mapping that is logical, and that's the mapping of every point into its equivalence class. So that's why it's called canonical or natural, is it emerges naturally once the equivalence relation is given. And But the question still remains is what's the topology of the quotient space? We know the topology of the real line, but the topology of the quotient space, we don't have one. Remember what the topology is. The topology of R of the quotient space is going to be a set of all open sets. And we know the rules for open sets. You know, they have to have this infinite union has to be an open set, finite intersection has to be an open set, the entire set has to be an open set, and the null set has to be an open set. And so we need to create this collection of sets. We need to invent this in order to make this a topological space instead of just a space. And so what logic do we use to create that topology? All right, so to understand this, we are going to go back to something we talked about a little bit earlier in the context of fiber bundles. We consider a couple functions. Consider a function from a set X to a set Y, and consider the case where we actually know the topology of Y. So we know that Y is a set Y with a topology of Y. And this was the case with our fiber bundles, right? With our fiber bundles, we had the fiber bundle itself was E, and then we had this projection map to a base space B. And base space, we knew the topology of B, or we typically know the topology of B, but we don't know the topology of E. So what did we say? Well, we said, well, we want to create a topology on E that would be the coarsest, so pi is continuous. Well, that means that pi inverse on any open set of B must be an element of the topology of E. And this is called the initial topology. So the initial topology on the set E is designed only with the intent of making the projection map of the fiber bundle continuous, right? And it's the coarsest topology. It turns out we're just going to take every open set of B, take its pre-image, and throw that in the topology of E. And it turns out that if you do that, and you can work on this one, you can look this up, but you can, if you examine how this works, that does form a topology. The intersections and unions of sets here are appropriately intersections and unions here under this topology. So this actually is a topology called the initial topology. With the quotient space, so that was from our example of fiber bundles, right? That was how when we had a set whose topology we didn't know, we created it using this rule here. And we created something called the initial topology. With our quotient space, we're kind of in a different situation. We're in the situation where we have a map between X and Y, where this is, in our example before, this is the real numbers with the topology on the real numbers, and Y is the quotient space. So in this case, we have a topology on the domain, but not on the range, right? Or I shouldn't use those words. We have a topology on the, well, yeah, so we have the topology of the domain and not on the range. So that's the opposite of this case. So we can't use the initial topology, but we can use something called the final topology, which is very similar in motivation. The final topology is going to be not the coarsest function, but it's actually going to be the finest topology. So, and we call this P, here it was called pi, right? We're going to call this P. So P is continuous. You see, all we have to work with, if you go back to our previous screen, is this function P. So we have a topology here and a function. We need a topology here. We don't want to just create things arbitrarily. We want to use the tools that we have. instead of inventing ad hoc topologies. So we're going to make a topology that is just sufficient so that P is continuous. And what does that mean? That means P inverse has to map open sets from the quotient space into open sets of the base space, the underlying space, which was the same condition when this was the total space of the fiber bundle. Pi had to map open sets of the base space into open sets of the bundle space. So the situation's identical in requiring the continuity of this map, the map going backwards of this map, P inverse. That has to map open sets from here into open sets up here. The difference is that in the case of the fiber bundles, we knew these open sets and we didn't know these, and in this case we know these open sets but we don't know those. Right? That's the distinction. So the final topology is the finest topology, so P is continuous. So I need all of the sets in Y such that F inverse of O is an element of the topology of R, right? And once I've identified all of those sets, all of the sets in Y, such that the inverse under, well, I guess I should say P inverse, sorry, those sets are going to be the topology of the quotient space. And that topology will make sure that the projection map P, the natural projection map, is continuous. And that's called the final topology. Now, one part of the final topology that always confused me was this word here, finest topology. And what's interesting is how coarse and fine, because this was the coarsest topology in the initial case. So in the final case, you go to the finest topology. And it kind of stands to reason that if, when you think carefully about it, why that would be the case. If you have a topology here that's extremely fine, like say the discrete topology, say every element of this set was open, then the inverse projection into X could easily end up yielding sets that are not open in X, because it's so fine here that X is too coarse to measure every one of these open sets under the inverse image of P. So a single point in Y might project into X in a way that is not open. In fact, that's a really good example here. If we go back to here, say I take a single point in the quotient space. Say I took this point. I took the quotient space. One element of the quotient space is a set, and it's a set of all these points. Well, if I put the discrete topology, which is the finest possible topology, if I put the discrete topology on the quotient space, then every equivalence class would be open. And so what's the inverse of the projection map of that? Well, the inverse projection map would be X, 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 all of these points, right? Well, the union of all of those points is not open in R. It's not, because R does not have the discrete topology. R has that closed ball topology. So these points aren't open in R. So a discrete topology on the quotient space is too fine, because under the inverse map, an open set in the quotient space does not map to an open set in the already existing topology of the real line. So I need bigger set. I need a coarser topology on the quotient space, and in order to get this to work. So that's why in the final topology you're dealing with the finest topology. In this case, you're dealing with the coarsest topology because you're sort of in the opposite situation. Right? You're looking for a topology here. Well, I could make this the discrete topology, right? And if I made this the discrete topology, any inverse mapping, every single inverse mapping would be open in E, and that's overkill, right? That's it doesn't really tell us anything. So we're looking for the coarsest, the roughest mapping that allows this continuity in this case. So in here, being fine actually hurts us. Here being too fine hurts us, and here being well, I guess in both cases, being too fine hurts. Okay, so that's the distinction between the initial topology and the final topology. And we are going to actually use the final topology on our quotient space. And that's the topology we're going to use to topologize that space. All right, and now also while we're on this subject, we might as well knock out another quick point. If I have a map F from a set X to Y, and we're going to assume these are both topologized spaces, which is fine because now we kind of have a sense of how we're going to do it. So this has the topology Tx, and this has the topology Ty. And with this, we are going to ask the question, is F an open map, or is it a closed map, or neither? It doesn't have to be open or closed. But an open map is pretty clear. An open map takes open sets of X and maps them, well, let's put it this way, and the mapping of open sets of X are open sets of Y, and likewise, the mapping of a closed set, I'll call that maybe C, is closed in Y, which there's really no totally trivial way of writing that, so I'll just say f of C is a set in Y and it's closed. So that's an open map, that's a closed map, and they don't have to, if you're open, you can be one, the other, you can be neither, but it is an important concept. Now, this is different from continuous, right? Continuity, remember, has to do with not whether F maps open, whether F is open or closed, but F inverse has to be an open map in order to establish continuity. So you can be continuous and not open, and you can be continuous and not. I mean, there's all these possible combinations. These are different concepts, but continuity, it's important to remember, always leans on the inverse. The continuity of a function always depends on the inverse mapping. All right, so that's what open and closed mapping are. This allows us now to define the quotient map. Notice we've already established the canonical projection P. Now the question is do we have a quotient map? And a quotient map has to be surjective, which means it has to be, the other word for surjective is it has to be onto, right? It does not have to be one-to-one necessarily, but it has to be onto. It has to be continuous, right? And it also has to have this property where P inverse, right? P inverse of a set U is open then U is open, right? So remember, we have our set A, we have the canonical projection P to A over the equivalence relation, right? So we have this mapping. P inverse goes this way. So if I have any set U inside A, P inverse of U actually, P inverse of U is a set in here, right? If P inverse of U is an element of the topology of A, that must imply that U is an element of the topology of God darn it, of A by the equivalence class. And so this is a bit of an awkward way of looking at things, right? Because it's not really a definition of continuity, right? If you have an open set here, P inverse has to give you an open set here if P is continuous. So if we use the final topology will be okay in that regard. Any open set in the quotient space under the inverse projection, its image will be open here. That's good. But that's not exactly what this rule is saying. This rule is saying that any set that I have over here, if I do the inverse projection, then if it's open here, that set must be open. So you can imagine finding an open set here that is the image of a set here that's not open, right? In which case, you would not have a quotient map, right? So the quotient map has to be surjective, continuous, but it also has to mean that the preimage of every open set here has to be open over here. Is that right? So if I, well, I guess that's not correct, right? Because I got to be more careful. It's any set in this space, in the quotient space, that has an open preimage in the underlying space, right? Then that set must be open, right? And that's not quite the same as all these other things we've talked about. And so that is what defines a quotient map. And we're going to run through a couple proofs where this issue becomes kind of important. But with this quotient map, we can now create the quotient topology. The quotient topology is how we're going to topologize the quotient space. And that quotient topology, which would be T, in our case, I guess it would be, let's be more abstract. T, A by some equivalence relation is going to be the set of all subsets of the quotient space such that let's move it this way so you can see it, such that U is actually the union for every equivalence class that's an element of the set U this is going to be an element of the topology of A. So the way this works, wait, sorry, this part doesn't make sense. Okay, so the way this works is a subset of the quotient space is an element of the topology of the quotient space if we can go to that subset, right? Go to that subset U, look at every element of the subset. Now remember, U is a subset of the quotient space. So U, the quotient space, is a set of elements of equivalence classes, right? It's a set of sets. So I go to every equivalence class that's contained in this nominee set U, where it's a nominee to being part of the topology. And I take each of those equivalence classes and I take the union of all the elements of the equivalence classes. So what that does is that effectively takes a set of sets, right? And it creates just one set, one big set of all of the points that previously lived in all these little sets. I take the union of all these little sets and I create one set. Well, the members of each of these sets are actually part of the underlying set A, right? So this set here is a subset of A. It's no longer a subset of the quotient space. This union of the way I've constructed this union, this is a union of all these equivalence classes and all the elements of these equivalence classes together. That has to be an element of the topology of A, right? And that's the quotient topology on the quotient set. So with the quotient map, we can define a quotient topology just like this. Oops, I just noticed I forgot the closing bracket on this set here. Okay, so with this quotient topology, now we can start thinking about we can talk about these spaces slightly differently. So I'm going to just be a little more abstract now, and there'd be a space A, which in our initial example was these real numbers, right? And then we're going to have another topological space. I can now call it a topological space because we're going to give it a topology, the final topology, the quotient topology, and this natural projection P is this projection operator. Now, and this is all going to be based on an equivalence relation of some sort, right? So we know that out there exists some equivalence relation, which I'll call this tilde. And now, one thing that's interesting is there is a little bit of a call out to fiber bundles here, because if I take a point in A, right, and actually the other way around, right? Sorry. If I take a point in this space, right, in the quotient space, and I find P inverse of that point, call that point X. If I find P inverse of X, there's just a whole bunch of things in A that map to the point X. And so the inverse mapping from X to here, this starts looking like a fiber over X, where this kind of looks like a base space, and this looks like a fiber bundle. It's not exactly that, of course, because there's a lot of other things that make a fiber bundle that we haven't verified are here. But nevertheless, this inverse projection of a quotient map is sometimes called the fiber over X if this is a quotient space, right? In a fiber bundle, the base space does not have to be a quotient space of the total space, right? But when we're talking specifically here about quotient spaces. But a quotient space definitely has something similar to a fiber bundle in that the inverse of the projection map, it has a projection map, for example, right? This equivalence relation defines this natural projection map for a quotient space, and the inverse of that projection map does give us something that kind of feels like a fiber, right? And we do know, by the way, that if I have another point, y, right, that one under the inverse projection map will also be a fiber, and we know that there will be no intersection between these because the equivalence relation is guaranteed to partition A and partition it into disjoint sets. So, you know, it really does have the strong appearance of a fiber. Now, we should say something about the properties of this space if we know the properties of this space. And the answer is that this is not a quotient map is not a homeomorphism, right? And so a quotient map is not the same thing as a homeomorphism. Now, the homeomorphisms were used special because they preserve properties. If I have a property of this space here, if I have a property of this space here, then if this was a homeomorphism, it would have the same property in this space. This property, so for example, if this one had a certain type of separation, say this was Hausdorff, then we had a homeomorphism, this would be Hausdorff. If this was connected, then this would be connected. If this is path connected or simply connected, this is going to be path connected or simply connected. The dimensionality of this is going to be the dimensionality of that. If this was a differentiable manifold and we could define dimensionality, then a homeomorphism would preserve it. Quotient maps don't really preserve any of those things. The separability of this space could be different than the separability of this space. It turns out if this space is connected, then this space will also be connected, so that's a property that does get preserved. But if this is simply connected, it's not guaranteed that this will be simply connected. So that's important, right? I mean, that's a topological property that is not preserved by the quotient map. And the dimensionality of this space does not have to equal the dimensionality of that space. So quotient spaces can be extremely different as from the underlying space. So an important definition we're going to need for another interesting proof we're going to do, or example, is the idea of a saturated set. A saturated set only makes sense in the context of it makes sense in the context of these equivalence classes. in the equivalence relations, but also quotient maps. So if I have a set, I'll call it A, and a quotient map to a set B, and likewise it could be based on an equivalence relationship, in which case this set is A, is the quotient set, right? A quotient map does not necessarily have to be based on an equivalence relation, but it just has to have those properties. Well, it has to be surjective, right? It has to be surjective. It has to be continuous. And 3, it has to have that property that the inverse of a subset U in the quotient space, if that is an element of the topology of A, then U is an element of the topology of essentially the quotient space, right? It has to have those properties to be a quotient map. And it turns out that the mapping, the natural projection based on an equivalence relation will have all of those properties. So, but a saturated set is a set in A, so a saturated subset of A is what we're talking about. It's going to be saturated if A is essentially the union of equivalence classes, right? If U, let's call that set U. If U is equal to the union of a bunch of equivalence classes where an assortment of equivalence classes of A, then U is called saturated. The other way to think about it is, since every point over here in this set, every point over here represents an entire equivalence class. If you take the inverse for each of these points, and this subset U is completely determined by the union of pointwise inverses of points in this class, then this thing is in this set B, then this is going to be called saturated. So a saturated set, saturated subset of A is just a subset that is in itself the union of perfectly the union of a bunch of equivalence classes, no more, no less. And that is called saturated. And the reason saturated sets are important is you can prove that the image of a saturated set under a quotient map will be open if the saturated set itself is open. So in this case, if U was an element of the topology of A, and U is a saturated set, then PU is open in the quotient space. That is, if P is a quotient map, right? P has to be a quotient map. It has to have those properties. And if that's the case, you're in good shape, because what this means is I can look over here in A, and I can find a saturated set, and if P is a quotient map, I know I'm going to end up with an open set in B, as long as B has the quotient topology. Right? That's important also, right? We have to put the quotient topology on B, but that's what we're going to do. Use the coarsest topology that makes sure that this map here is continuous. So this is an important principle. If I have a saturated set in the underlying space, and I drive that saturated set into the quotient space using the natural projection, then I end up with an open set in the quotient space. And that does not mean that P is open, right? An open mapping will take any open set from A and give you an open set for B, but that's not the case here. Only saturated open sets in A are guaranteed to map to open sets in B. If B is the quotient space, the mapping is the quotient mapping, and we assert the quotient topology on this. So there's a lot of conditions that have to be satisfied. But if that's the case, then if I have a saturated map here, a saturated subset here, I will get an open set over here. All right, so that's really important. Now from this, we can start to think a little bit more about our original example. So let's go back to it, and I will now draw it again. This is the original example we started with, and then we went back off into some topological definitions, and now we're coming back to it, right? 0, 1, 2, 3. When I did the first presentation of this, I broke it up into 2 pi and pi. I'm going to drop down to the integers right now, and we're going to look at this as the real line with the topology of the real line, right? And I'm going to create two different mappings. The first is a mapping into S1, the circle, right? This is this S1 with the usual topology of S1, which is open intervals. And I'm going to think of this in terms of a coordinate axis, I guess, like on the plane. And I'm going to call this mapping Q, right? And then, on the other hand, I'm going to create another mapping, the natural projection mapping of the equivalence class, where we're dealing where x is equivalent to y if y equals x plus some integer n, where n is an element of the integers, right? So this is going to be the equivalence relation, and that equivalence relation is going to automatically spawn a canonical projection, and that's going to land into some space here that we're going to call R by the equivalence relation. Now in this case, sometimes there's actually a way of looking at this in terms of groups, where this becomes what we call an additive group of homeomorphisms of the underlying space. I'm not going to do that, but sometimes if you run into that when you're studying, you'll see this space referred to, in that case, as R Z by the integers, where Z is a subgroup of the homeomorphism group of this line. So you take every possible homeomorphism of this line. One subgroup of those is addition by integers, and I can partition. I can create an equivalence class based on the action of that subgroup, and I end up with a symbolism that looks like this. But it's the same thing. I've established the equivalence class in the same way. So the point is that this here becomes, I guess, what we would kind of call, well, that's the quotient space. This is the quotient space. Now, the only reason we do quotient spaces is we like to be able to construct things that are kind of interesting out of other sets, right? But this is not the quotient space. This is, and this is some sort of unknown object. It has a quotient map and a quotient topology, but what I'm interested in is showing that these two are homeomorphic. That is, this is homeomorphic to the quotient space. Because I can create a map from this to the line, and in fact I should do it. The way I'll do that is I'll write Q, so say this is T, this is T, the variable here is T. So Q of T equals, well, I want to write e to the 2 pi I t, like that. The problem there is that that's a complex number, of course, but let's assume that I make this the imaginary axis and this the real axis. Yeah, then we're fine. So that's what qt is. Alternatively, if you want to think of it in terms of real number, q of t would equal cosine of 2 pi t sine of 2 pi t. That would do the same thing. And then we could do two real axes. Either way, that's equivalent. So this is a legitimate mapping, right? That's all squared away. This is a mapping we understand because this is literally the mapping we did before, except now it's in integer. So I don't have a 2 pi times an integer. I just have an integer. So I've just kind of straightened it out to integers. That 2 pi, by the way, is landed over here, right? If I had done it some other way, this would have just been cosine of t and sine of t, and then the 2 pi would have been over here, something like that. So the question is what is going on here? Can I show that these two are homeomorphic? That's what I want to show. So I'm going to start by showing that if we take an open set here, there's an open set there. We'll call it U. I haven't used U here on this page, I don't think, so we'll call that U. And that's open in the quotient space, and it's open based on the quotient topology. So the point is, I have an open set. I'm stipulating that U is an open set in the quotient space. So I know that U in the quotient space is going to map back up here under P inverse, right? And by the definition of being a quotient map, right, then I know that a quotient map with the quotient topology, I know that, what do I do? I guess I'll write P inverse of U, which is going to be up here. I know that that is going to be open on the real line. And in fact, in this particular case, if I have a collection of points here in the quotient space, I kind of know what this is going to look like, actually, right? This is, one point is going to graph to these points like this, everywhere sort of in between the integers. But a whole bundle of points is going to graph to a bunch of intervals that are all the same. Like that, maybe. And the union of all those intervals is definitely open on the real line, right? The union of all of these intervals is an infinite union of open balls, and the open balls are the base of this topology. So I know that that's kind of what it's going to look like. But what's important is I know that the inverse mapping here is going to give me an open set up here because of the definition of how the quotient topology works. It is a quotient of the quotient map, and the quotient topology forces that to be the case. So now, what's nice is this mapping that I've chosen that goes this way. It does actually kind of the same thing, right? I know that if I know that each of these intervals is going to map to the same interval on this circle as well, right? So I know that I'm going to get something like that for, say, these intervals that I've plotted up here under Q. And furthermore, I know about Q. I know that Q inverse, all open sets here are going to map to open sets here. So if I have an open interval in the S1 topology, maybe I should make it clear what that is. It's kind of a little odd, but this whole set here is S1 with the standard topology of S1, which are these intervals, which are these like little open interval. Well, the base of the standard, I should be more precise, the base of the standard topology are these open intervals all around the circle, and that's the base. So again, infinite unions and finite intersections are all in the topology as well. But I know that Q is continuous because Q inverse, if I take an open set in this topological space and I use this mapping in the inverse form, I end up with this string of open intervals which is open in R. So I know that Q inverse maps open sets to open sets. Therefore, I know Q is continuous. So far about Q, I know Q is it's 1-to-1, right? I'm sorry. What am I saying? Hold on. Q is surjective, right? Meaning that the entire target space is covered by mapping from the underlying space, or the domain space entirely covers the range. So I know it's surjective, and I also now know it's continuous, right? And now there's a third condition that we need. What we're going for is we're trying to prove that Q is a quotient map, right? And so the third condition we need has to do with if the preimage of a set in S1 here, if that preimage is open here, then that then that original set must be open here. Remember how that worked? It was something. It was a little more subtle than continuity, right? But we can actually see how that would work, right? If we know what the open sets are here, right, and the preimage of this open set, for example, the one I'm highlighting, the preimage of that is going to be exactly this. So we know that this particular open set is the preimage of an open set in S1. So that works just fine. And in fact, every open set in S1, if I took this and I took the union with, say, another little open set over here, that would end up, I would just add those in up here like that, and that would still be open in R. So now I could say this open set is the preimage of this set here, and that, sure enough, this is open and that is open. Therefore, therefore the preimage of an open set is open in R. The preimage of an open set in S1 is open in R. However, think of this set. If I went with this blue, say I just went here and I have this one interval, right? Just that one interval. And well, what is the mapping of that one interval through Q? Well, the mapping of that one interval through Q is still going to land somewhere on the circle, right, through Q. So that would be Q, if I called that A, that would be Q of A, say. Now, the problem is that the preimage of the Q of A, the preimage of the Q of A is not just this, but it's also one of them in every integer segment. So here's an example of an open set in R, right, whose that is not the preimage of an open set in S1. And so that's just goes to show that not all open sets in R are preimages of open sets in S1. But that's not the requirement to be a quotient map. The requirement is that if the preimage of some set in S1 is in fact open in R, then that set in S1 better be open in S1 for this to be a quotient map. But regardless, in this circumstance, you can see that all the preimages of all the open sets of S1, all the preimages are going to be open in R, and therefore we have that condition. We have the condition that Q inverse of O is an element of the topology of R, implies that O is an element of the topology of S1. And that means that Q is a quotient map. Right? We've got the three conditions we need for a quotient map. So that's important. So why is that important? Well, it has to do with this notion of saturated sets. So what's happening now is we now want to realize that every instance of this mapping corresponds to exactly one instance of this mapping. The way we say that is that P of T equals P of S only if the equivalence class of T equals the equivalence class of S. And that will be perfectly in one-to-one correspondence with e to the 2 pi I t equaling e to the 2 pi I s. So what we can show is that these instances of these mappings for points are in exact correspondence one-to-one with instances of these mappings. And the reason that's important is because if you look at the inverse projection of an open set U, right, which was these red lines initially, right, so we're going back to that first, the image of an open set from the quotient space, the image of the preimage of that open set in the real line, these are saturated. This preimage is saturated. And it's saturated because every point here is an equivalence class. And this preimage is just the union of all the equivalence classes that are jammed into this open set U. So these are all saturated. But remember, if an open set is saturated, then a quotient map takes it to an open set also. So this is a quotient map, right? And all of these things are in play. So this is a quotient map. So I now know that Q is actually an open mapping, right? Q is an open mapping from, well, Q takes these open sets to open sets over here, which basically puts these open sets in one-to-one correspondence with these open sets, right? And that's important. And that's important because now we know that P inverse, or I should write Q after P inverse, right, which is this mapping after that mapping, Q after P inverse of an open set is an element of the topology of S1, which means, and P after Q inverse, this thing here, that's a mapping that goes from S1 to the quotient space. And we call that's Q after P inverse. And that mapping takes open sets from here to here. Now I can use the same logic and show that P after Q inverse also, which goes this way, also takes open sets from here to here. And once I have that, and plus these other properties that it's one-to-one and on-to, these are homeomorphisms. These are homeomorphisms. And so that means finally, which is the whole point of all this, that this is homeomorphic to that. And the proof is very windy, right? We had to use the definition of the quotient mapping, the quotient topology, and the quotient space to get from here back to here. We had to use that this particular mapping, which we just hunted down, right? We just made this mapping, and we made this topology because we kind of know the topology of the circle. And we know this mapping turns out to be a surjective continuous mapping where the pre-images that happen to be open sets in R are pre-images of open sets in S1. So this was a quotient map. And using that fact and the fact that this mapping is in one-to-one correspondence with this mapping based on the fact that every point in this circle maps to an equivalence class here in the same way that the literal equivalence classes of the quotient space map to the real line. Using all those facts together, we're able to show that that this map and this map are both continuous, bijective and bicontinuous and bijective, and therefore we have a homeomorphism between the quotient space and the circle. So when we say that the real line under this equivalence relation is the circle, what we really mean is the real line under this equivalence relation gives you a quotient space, and that quotient space can be shown to be homeomorphic to the circle. And so that's what all this stuff actually means when you dig through it. And and they usually kind of skip this step in a lot of physics books. Not the math books generally get it, but even they eventually stop talking about this, and they talk about this as though it is the quotient space. Technically, this is not the quotient space. The quotient space is a set of sets, right? That's what the quotient space is. A set of sets, where each of these sets is an equivalence class of something. And with the standard caveat that it's not usually not even a countable set of sets like I imply here, right? Countability. But the quotient space is a set of sets. It just so happens you have to work to turn that quotient space into something homeomorphic to another topological space. And then you can say, then once you feel like you've done that, once you're convinced that this topological space is homeomorphic to the quotient space based on all of this with the quotient topology and the quotient mappings, once you believe all that, then you can say, yes, the circle is the quotient space of the line with this equivalent relation attached to the line. And so that's kind of how that works. So eventually we're going to use this logic to create Mobius strips and all these other fascinating topological objects that are also differentiable manifolds. Oh, and another reason why this is important is if I had replaced all of this, with a different set, if I had replaced it with this set here, right, say 0 and 1, like that. Like I said before, this set that has a one-to-one correspondence of points in this set to this set. The problem is the open sets on this kind of interval, the topology of this interval isn't going to jive with everything, and therefore this is not the quotient space of this line. This is this thing here is a one-to-one correspondence, and it will represent every element of the quotient space. But topologically, it's not the same as the quotient space. We would have to give this a topology to capture this first point, and that once we do that, this mapping Q, whatever mapping we take from the real line to here, is going to fail to be continuous in one way or another. And so this is the wrong answer, which is why we went through this exercise, is to show that this is the correct choice, not this, not this. Now, I can't resist showing a dysfunctional example. And I shouldn't really say dysfunctional. It's a little unfair to the set we're going to talk about. But imagine the same real line with a slightly different equivalence class, equivalence relation, I should say. So I'm going to do the same real line with all these integers, but I'm going to say that x is equivalent to y if x and y are both integers. Right, so this is different than what we did before. Right now, the only members of the equivalence class, well, x is equivalent to y means 3 is equivalent to 2, is equivalent to -1, is equivalent to 0, is equivalent to 1, 2, 3, etc. forever, right? All of these are equivalent under this relation. But otherwise, x is not equivalent to y, which means all of these other points, every other point on the line, is only equivalent to itself, right? Or, well, if I guess I should write if x and if x is not an element of z, then x is only equivalent to itself, right? Something like that. But the point is I'm saying that all of the integers are in fact equivalent, and maybe I could do that this way by drawing it like this. All the integers are equivalent, and every other number is there is no equivalent pairing, right? So now, but that is still an equivalence class, because you'll notice that I can check, right? X is equivalent to y means x and y are both integers. Well, y is equivalent to x, so it's reflexive, or it's symmetric. Certainly, if x is an integer, then it's equivalent to another number that's an integer, so it's reflexive, and it's transitive, right? If x is equivalent to y and y is equivalent to z, then x and y are integers. Whoops, y and z are integers. Therefore, x has got to be equivalent to z. So it's definitely an equivalent relation, right? Because it satisfies reflexivity, symmetry, and transitiveness. So despite the fact that it's very asymmetrical in how it handles these numbers, meaning the overwhelming number of numbers on the number line are singletons have an equivalence class that's just one element, the integers have a countable infinity of elements. So, but it is an equivalence class, so therefore we can make a canonical mapping, and that canonical mapping, let's say, takes, I should make it red, I guess, right? it takes all of the integers to this point here. So that's sort of the equivalence class of 0. And then now we have to start working hard. From 0 to 1 are all these numbers, right? So they get mapped into a set. So I'm going to sort of hint that the way to draw this is it starts at 0, goes and comes back to 0, to the equivalence class of 0. It really comes back to 1, but 1 is equivalent to 0. So I've got to draw this interval here like a loop. The problem is when I get to this interval, it's also a loop, but it's not the same loop. It's a different loop. Because if it was the same loop, that would imply that, say, this point here at the midpoint was equivalent to some other point in this interval, probably the midpoint. And I would just put it all in the same loop, and we'd be back into the situation we were in before when we were dealing with the additive integer group creating the equivalence class. But in this case, we don't have that. We only have the integers are equivalent. So every interval is going to have a loop, right? I don't even know, I mean, how do you draw such a thing, right? You would have to draw loops like this, and there's an infinite number of them. And all of the loops would go and begin and end at this central point, and this central point is defined by the equivalence class of the integers. So that's a really different topological space, totally. It's totally a quotient space, but it's very, very different from the simple circle that we had when we did the additive group. Now, it turns out that this space, this real number with the topology of the real number, this thing here is first countable, right? It's second countable, and it turns out that this space is not even first countable. It's not even first countable. There's a wonderful proof showing that this is not first countable. I probably shouldn't go into it right now, but and if this isn't first countable, it's not second countable. If you're not first countable, you can't be second countable, it turns out. That is inherited, right? Not all topological properties are inherited, but this is one that is. So it's not first countable, so it's not second countable, but this is both first and second countable. But this equivalence relation, which gives you this wacky thing, doesn't preserve that property. So this just shows you how strange these quotient spaces can become. All right, so that's it for quotient spaces here. The next lesson we're going to do is going to cover how to consider quotient spaces to make the cylinder, right? The cylinder, to make the Mobius strip, and these little things I'm drawing here are sort of indicative of what that looks like. Then the projective plane, and how those are manifolds. That, I think, is going to be the topic of our next lecture.